So at this point, I would like to introduce Curtis Hinman from Herrera, who is going to talk about research. Thank you, Curtis.
Great. Thank you, Heidi. All right, so we're going to start off with a little background, water quality treatment and permeable pavement. And as it turns out, we've got a fair amount of history around the world on permeable pavement research, particularly from Europe. They've been installing permeable pavement for quite a bit longer than we have. So we have some research from Europe and some interesting longer-term research that we'll talk about at the very end. We also now have more research on water quality treatment and hydraulics as well, but particularly water quality treatment in the United States that's over the past 10, 15 years and really helpful in determining how well these systems work. So we're going to start off with just very briefly on treatment mechanisms, and then we'll spend the bulk of the time on initial and long-term performance. At the very end, we'll talk a little bit about long-term performance. To start off, just a little bit on treatment mechanisms. And there are several treatment mechanisms active in permeable pavement systems. Always at the top of my list is stormwater volume reduction. We've seen very good stormwater volume reduction in permeable pavement systems, even in very poor subgrade soils with low infiltration rates. And of course, treatment, when talking about water quality treatment, that soil receptor, the type of subgrade soil, will be an important consideration there. Reduce spray and vehicle wash-off. You perhaps have seen pictures of permeable pavement systems with much less spray coming up off the road than typical impervious roadways. And so that would also mean less water hitting the undercage of vehicles and washing off pollutants. Biological degradation, this is one we often don't think about. Permeable pavement systems do have biological activity that can work on hydrocarbons, and we'll look at some research from England on that. Filtration, of course, that's why these things clog, right? Why you have to clean them. Adsorption and volatilization. So quite a few treatment mechanisms present in permeable pavement systems. Pollutants that we're typically concerned about on pavements, of course, hydrocarbons, polycyclic aromatic hydrocarbons, for example, byproducts of the combustion engine. Metals, of course, sediment, nutrients, chloride, bacteria. Kind of a special mention to chloride here. Very difficult to treat. Really, source reduction is the best management for chloride. And we'll talk a little bit about this in the context of salting and how permeable pavement systems seem to behave in colder climates. All right, so with just the briefest background, let's look at some research from a couple different parts, in this case from Europe and from England specifically. And just to start off, permeable pavements appear to be highly effective at hydrocarbon biodegradation. And this is some research from Pratt & Newman. Let's start off by looking at the lower graph. On that lower plot, you'll see time in days. And then on the vertical axis, a mass of oil. So these were test plots that were located outside, full-scale test plots, as well as some laboratory rigs inside. And on both of these, they added oil and then applied sort of synthetic storms. You can see the trend line going up. That's the mass of oil added over time. And then on that horizontal line at the bottom is massive oil in effluent. And essentially we're seeing nearly 100% removal of hydrocarbon. And at the same time, Pratt & Newman were looking at microbial activity or count within the permeable pavement systems and found that that microbial count tracked very nicely with the addition of hydrocarbons to the system. So they'd add hydrocarbons and that microbial count would go up. Hydrocarbon concentrations go down, so would the microbial populations, and so forth as they proceeded through the experiment. So there are organisms living in permeable pavement, and they seem to be quite effective at degrading hydrocarbons. Next, let's take a trip over to Northeast United States, and this is the University of New Hampshire Stormwater Center, our best LID research program for cold climate, I think, in the region, although there's some great work going on in Colorado as well that Chris will talk about. What they found in installing permeable pavement in their campus is a significant reduction in the need for salt to manage ice in their parking areas. And they're estimating that their salt use may be reduced by about 70% by allowing that snowmelt and rain to infiltrate rather than freeze on the pavement surface. And these are pictures from University of New Hampshire taken at the same time, one on a pervious concrete installation and on the lower photo, impervious parking area. You can see the obvious difference between the two. And again, as I mentioned early on, really for chloride and salts, source reduction really is the best management approach. There are really no good treatment mechanisms for chloride, for example. So source reduction is the key there. All right, so back to the Pacific Northwest. And this is a study that was conducted by Booth and Botebo at University of Washington. And this is a material handling yard for King County located in Renton. And so this is a really industrial site. They took out some conventional parking spaces and installed some permeable parking spaces. These had about 90 to 100% occupancy during the business hours. They're looking at, in this case, dissolved metals, which is good, rather than just particulate. These test plots are about 6 years old. These test plots consisted of different types of permeable pavement. One, up top there, you see gravel pave, which is a flexible plastic grid system filled with gravel. Grass pave, same plastic grid system with grass. Turf stone, eco stone, a permeable paver, and then conventional asphalt control. And you can see that we're looking at copper, a dissolved copper, micrograms per liter, dissolved lead, dissolved zinc, and motor oil. And that MDL is minimum detection limit. And you can see for motor oil, for example, it's 0.1 milligrams per liter. So you can look across the bottom here and see the conventional asphalt and the concentrations collected from those plots, and in comparison to the permeable pavement. And you can see quite good performance. Copper, dissolved copper, for the most part down below one part per billion. Very good results. Lead, non-detect, very low levels. Zinc, good performance there. And motor oil, below detection limit. So these are some interesting studies. This is one of the first study from Pacific Northwest region indicating that permeable pavement might be offering some good water quality treatment as well as good flow control. So that's kind of a quick romp around studies in the U.S. and one from Europe. I'm going to spend most of the rest of this time on research that was done that I conducted along with others at WSU. This study is using full-scale replicated porous asphalt plots. The study objectives here were to assess the pollutant capture capability of a porous asphalt wearing course, so just the asphalt pavement itself, along with the pollutant capture capability of the aggregate base material underneath the pavement. And as I mentioned, this is somewhat unique research in that we had full-scale replicated research plots. So this is a parking lot with full-scale parking stalls, travelway, and those plots are replicated. We dosed these cells with synthetic stormwater. We created our own storms during dry periods. We used roof stormwater as the basis, what we would apply with our sprinklers. We applied street dirt that we collected from the city of Puyallup nearby. We spread that on the pavement at a known quantity onto the pavement. We applied dissolved contaminants. We sprayed those onto the pavement. And we collected flow-weighted samples from the under drain and a whole sample from the elevated drain. And you can see from the photo on the top the under drain at the bottom, and then the elevated drain, upper right, and that drain is located just under the pavement. And then there's a V-notch in the center there to collect any water off the pavement. And of course that's where we would collect our samples for the impervious asphalt, but we never really collected any samples. There were no samples that came from the porous asphalt. And you can see that these were lined. These were lined cells on the bottom. You can see the cells lined with rubber liners sealing those cells off. We applied approximately 1,700 liters per cell at an approximate rate of 850 liters per hour per cell. And this approximated an application depth of about 32 millimeters. And you can see here on the bottom, we've got some tables of what the loads that we applied, concentrations and loads to these cells. And I'm not going to run through these. I just will let you know that we actually dosed these cells at quite high levels. So really, to a large degree, these were dosed at industrial levels. And as I mentioned, we had an elevated and under drain. Again, you can see the picture of that under drain on the lower left. On the upper right, the elevated drain. The wearing course, the pavement, about 10 centimeters, and the aggregate base underneath, 46 centimeters. And on the lower right, the large picture, you can see the spray apparatus, and it was actually quite sophisticated. So we measured very carefully the amount of water that we'd spray apply to each plot. All right, so that's just a little bit of background. What we'll do now is look at some of the results from those experiments. And again, why I'm spending some time with this particular set of experiments is that it really looks at the contribution of the pavement on its own and then the contribution of the aggregate base and separates the treatment capability of the two. So we're going to start off with some TSS, total suspended solids, and you can see there on the left of this plot, you can see the maximum number above 2,500 milligrams per liter, so quite high doses at time for TSS. But on the left is the impervious or our impervious asphalt cells. So we collected surface samples from the impervious asphalt cells, and then in the middle there, the pervious upper drain, so that's after the synthetic storm had just passed through the pavement, and then the pervious low drain, that's after the synthetic storm passed through the pavement and the aggregate base. And you can see in the tabular data above, off to the right of the plot, the median concentrations and very good reduction for TSS in comparison to the impervious asphalt, about 208 milligrams per liter, and the pervious upper drain down to 7 milligrams per liter. Interestingly, in this, we see a slight increase from the pervious upper drain to lower drain, and you can see the associated percent reductions with that, likely due to fine material washing off that aggregate base. So in this case, the TSS capture was actually best in the asphalt wearing course itself. All right. Let's take a look at phosphorus next, and I want to take a moment on this graph just to point out what, a little bit more detail on these plots, since we're going to look at a few more of these. Again, you can see the concentration milligrams per liter on the vertical axis, our impervious cell to the left, pervious upper drain and pervious lower drain across the bottom there, and then these box plots. The dark line within the box, that's the median value. That's the value indicating the central tendency of that data. The lower part of the box is the 25th percentile. Upper part of the box, 75th percentile. The bottom whisker, our minimum value, and the upper whisker, maximum value. So that just gives you a sense of what these box plots are telling us. They give you a good sense of the distribution of data as well as comparison between the two. All right, for total phosphorus, again, median value of our impervious asphalt samples, 0.7 milligrams per liter, and quite good reduction for total phosphorus, 0.1 for pervious upper drain and about the same for the pervious lower drain. And this is very likely due to the good particulate capture capability of the pavement wearing course, acting as a very good particulate filter. For orthophosphorus, or soluble reactive phosphorus, well, not quite so good. Median value for impervious asphalt, surface samples 0.2 milligrams per liter, and then down to 0.1 once it's passed through the pavement. And that next value is actually not zero. That should not read zero. It's actually just below detection limit, at or below detection limit for that sample. But quite good treatment for orthophosphorus. Interestingly, we're seeing, in this case, better treatment for orthophosphorus in our permeable pavement systems than we are in our current bioretention systems. Okay, total copper. Again, you can see the median concentrations for impervious asphalt at about 44 micrograms per liter. Very good treatment for total copper, down to 7 micrograms per liter once it's passed through the pavement wearing course, and about 84% reduction in that concentration from the impervious asphalt sections. Very good performance. Dissolved copper, well, not quite as good, although we have very low median concentrations that we're seeing in the impervious asphalt, 5.7 micrograms per liter, parts per billion. Once you start to get down to that level, those low concentrations, it's difficult to get lower than that. But we saw a slight reduction once that water passed through the porous asphalt, and then some slight increase once it passed through the aggregate base. Total lead, very good reductions. Again, from 23 micrograms per liter in our impervious asphalt down to 1 and slightly less than that after it passed through the aggregate base. 95 to 97% reduction. Very good very good performance. For lead and dissolved lead, also good performance, particularly considering the low concentrations in the impervious asphalt samples, 0.7 micrograms per liter, 0.7 parts per billion, down to 0.2 and then 0.1 once it passed through the aggregate base. What did we learn from this study? Well, it appears that in general the bulk of treatment occurs in the pavement wearing course for the particulate contaminants. And this probably should not be too big of a surprise in that we know that permeable pavement systems collect sediment in the wearing course. That's why we have to clean them. And so hopefully this should not be too big of a surprise. The TSS was an exception to that particulate contaminant behavior. And we saw an increase. Remember that we saw an increase from the upper to the lower drain. And again, this is likely due to inputs from the aggregate base. So this should indicate to us in general that we have to be careful and cognizant about the aggregate base that we use, and it should be quite clean. The more fine material there's associated with that aggregate base, the more we're going to expect that to wash off into our subgrade. We saw an increase in capture from the upper drain to lower drain for most dissolved contaminants, and so that aggregate base did some treatment and for the dissolved contaminants. And again, this probably would vary with the quality of that aggregate base. In this case, we had a fairly clean 3/4 to 1.5 inch crushed aggregate. We had that spec'd at no more than 2%, passing the 200 sieve. So for that particular material, we did see some improvement in treatment as that synthetic storm passed through the aggregate base for the dissolved contaminants. Very good treatment for most contaminants, except dissolved copper was nothing to get too excited about. We may be seeing some copper inputs from the aggregate base. We have tested some aggregates and found copper in those aggregates, so that wouldn't be a surprise. Okay, I want to finish up with a study from Europe, and the question that often comes up is if we're going to allow road runoff through that permeable pavement, how will that affect the aggregate base and subgrade underneath it? Are these going to become, sometimes you hear the word Superfund sites, are they going to become long-term contaminant cleanup problems? And so one of the best studies that we have out there is from Germany. At the time of this study, it was a 15-year-old supermarket parking lot. It's a permeable paver installation, and the researchers identified a parking stall that was still infiltrating and that had apparent heavy use. You could see oil stains on the pavement. And they painstakingly removed the pavers and essentially spoonful by spoonful removed the aggregate base and the subgrade beneath that. And we're looking at concentrations of copper, zinc, and cadmium for soils. So pay attention here. This is milligrams per kilogram. We're looking at soil concentrations, not water concentrations. And so after 15 years, we're seeing at about 15 centimeters copper, zinc, and cadmium at basically background levels. Of course, you can see elevated concentrations at the pavement surface and down to about 15 centimeters. And then very low concentrations below 15 centimeters. So this is a great study, one of the best studies we have for long-term performance, and suggests that these systems may be quite robust for managing pollutants, in this case metals, over long term. All right, so that wraps up my presentation.
Curtis, thank you very much. That was very interesting. Okay, so Curtis, there's a question from Jeff about clarifying how the upper drain works.
Great. Let's just go back to one of the pictures that I think will help a lot. So here, Jeff, on the upper picture, the picture on the upper left, is a picture of the porous asphalt cells. They're, as you can see here, they're divided. They have concrete dividers. Again, they're lined. But that's a picture of the upper drain. That drain is a 6-inch PVC pipe cut in half and then filled with aggregate. And then this cell is almost ready, not completely, but just about ready for asphalt to be installed right on top of it. So that pipe cut in half and lies just underneath the pavement.
So Jeff asked, so not all the water went through the upper drain then, in that case?
Yeah, so in the case, the upper drain would collect water from simply a 6-inch slice of the pavement. So it would, given that it was a 6-inch pipe cut in half, it would collect a 6-inch wide section of water flowing through the asphalt pavement.
Next step for the WSU site.
That's a good question, and you would need to ask WSU about that. And again, I am no longer with WSU and with Herrera Environmental Consultants, so I'm not sure of what their future plans are for the pavement. I know there have been subsequent experiments run on the pavement, and so there's more data now, but I'm not sure of future plans of different types of experiments they might be running. But that would be a great question to direct to the Stormwater Center there. Great, thank you.